Welcome today. This movie is specifically for current and future users of the USAXS instrument because what I want to show you is how to calculate uh, the expected scattering of your sample before you even come to the beamline, and because I have to do that as a part of it, also how to calculate the sample transmission so your sample has an appropriate thickness for the conditions with which we're going to be performing the experiments. This may be useful for other users of other instruments. I would hope that other instruments provide similar tools for their users, but the primary use of this is for the USAXS users, mainly the future ones who have not yet measured the samples and want to know if the samples will be suitable and how thick to make them. So when you apply for beam time at the USAXS instrument, one of the important things we need to know is what X-ray energy you want to use. We have a synchrotron, and our instrument can operate somewhere between 10 kiloelectron volts and 30 kiloelectron volts. About 28 is the maximum energy we normally offer to users. So let's assume that we would say that we will offer you two choices, 12 and 21 kiloelectron volts. Those are the standard energies which would be available. Most of the time we run at 21. 12 is perfectly fine. We can do that easily. It actually is very stable. And so let's say that you have these two choices and you need to prepare your samples. And I prepared here some examples of what your samples may look like. So I have decided that we're going to try to calculate about gold nanoparticles in water. That seems to be favorite for lots and lots of users for some reason. So we're going to calculate the gold nanoparticles in water, and we're going to assume that you have 0.1 volume percent of nanoparticles in there. That's significant loading because that's a volume percent, not weight percent. Then what I decided to try to calculate is chromium in nickel. Yeah, I know it's not realistic. If you have a chromium precipitates in nickel, it's going to be some kind of nickel chromium alloy, but let's assume that that's what it is. And let's also assume that we would be shooting for about 0.1 volume percent. That would be your reasonable estimate for your precipitates. We're going to play also with the sizes, so we're going to get to it a little later. And then for polymer guys, I assume that we have a hydrogel. So we have a water, H2O, in PVA, which I found on Google has a density of about 1.27 grams per cubic centimeter. That is the frame density of the polymer itself. We're gonna mindlessly assume that that is what it is. And then we will assume that the chemistry of that material is C2H4O, and that's the repeating unit. So there's a bunch of those in there, but actually it turns out this is good enough. And we're going to assume that in this case we have 80% of water, so these are water droplets inside a frame, inside voids in the PVA. So we're going to be using that as a contrast. Now let's assume that we can do the experiment at 12 kiloelectron volts or 21 kiloelectron volts. And what we want to know is what is the signal above the background of the USAXS instrument. Can we see it? How much we can see it? Also, what you want to know is what is the reasonable sample thickness for those two X-ray energies. And as a note, I here put that typically you want the sample transmission to be at least 20%. And if you do a little calculation, you can actually show that at given energy, the best signal to noise ratio is if you have a transmission of about 1 over E. Let's just hand wave to it to be 40%. Okay. So first thing what you need to do in this case here is use some of the IRENA tools to calculate the contrasts and transmissions. So if we go in SAS and we go in scattering contrast calculator, we're gonna save in this experiment the chemistry so we don't have to worry about the existing ones, and let's start. So we're gonna need 1 We need a gold. Someone stole my gold, so that would be somewhere around. I cannot find gold. Is that it? Yes, that's it. And we're gonna have a gold 1, and we're gonna save the gold. Then we need water. Water is, oh, sorry, back to the gold. Gold head density is 19.3. So save as a gold, and yes. So let's say gold 19.3 saved. We're gonna go and say we need chromium. Let's change the chromium. That's here. The density of chromium, we said it's 7.2 grams per cubic centimeter. We're gonna save and say this is a chromium. Then we need nickel. So let's change this chemistry to nickel. Is that nickel? Nope, that's niobium. Someone stole nickel. Here's nickel. And nickel is 8.9 grams per cubic centimeter, and we're going to save that as a nickel. Then we need H2O. So H2O has 2 elements. The first one is H. The second one is O. So it's 2 O's, 1 H. So we have an H2. Oh, sorry, 2 H's, 1 O. Okay, and the density here is actually 1, and so we save that and get an H2O. And then we have the PVA, so that's 3 elements. We need, first one is gonna be NaC2, next one is H4, and next one is O, and that is 1. So, and the density is 1.27. Okay, save, and let's call that PVA. Okay, so now we have all of our little elements we're going to playing with, or compounds we're going to playing with. Good. So the next thing what we want to do is we want to calculate the contrast, and turns out the easiest way to calculate that is actually using anomalous calculator. And so we're gonna go here. Let me make it a little larger so you can easily see it. So let's say we have water. I hold down Command key or Control key. Go on. Oh, Shift. So you hold down Shift key. So we're gonna go to 12 kiloelectron volts, and we have gold and water. So what is the let's first start with the contrast here. Let's recalculate. And now what you have is a contrast of gold against water. So that gives me a contrast here. So the contrast, I'm going to keep writing here. So delta rho square for AU H2O is 10 to 90. And, 10 to the 12, 10 to the 20, something, whatever. Then the next thing is we want a chromium versus nickel. So I'm gonna do chromium. Oh no, let's do the same one, except we're gonna now do the same thing at 21 kiloelectron volts. Recalculate, and you can see that is, and this is 12 kV, and then we have 21 kV. And notice it's much different because there's an absorption edge of the gold nearby. So the 12 kiloelectron volts is in the area where there's an absorption edge. I can show it to you. If you look on the range and you say 10 to 14 kiloelectron volts and recalculate your delta rho square, see how much it changes. At 10 kiloelectron volts is 12,000 and a change, and then at 10 kiloelectron volts at around 10 is actual absorption edge of gold, or about 12 is absorption edge of gold. So at this energy there's a smallest one, then you're above, And this is important because you don't want to be nearby the absorption edges for various reasons. Now let's keep going on the contrast here. So the next contrast we want to do is a chromium versus nickel. And we want to do 12 kV, and that's here versus there at single energy 12. Recalculate, and we have 223.6. And then we do 21 kiloelectron volts. And change that and recalculate. And we get 248. There's no absorption edge nearby here, so the difference is relatively small. Much smaller. Okay. And then we want to do the PVA. So we want to do PVA versus H2O. 12 kV. So that would be PVA versus H2O. 21. So that is 21 kV is here. And that one is 5.32. And then we go back to 12 and recalculate. And then we get 5.31. So there's no difference, no surprise here. There's no difference. But notice how much different those are. Your gold has a huge contrast. Nickel is somewhere midway with chromium, and then the PVA is very different. The next thing is we want a transmission, so we want to get the thicknesses. So for our system H2O versus gold, we can more or less assume that it's H2O. So transmission H2O. For 12 kiloelectron volts, so in this case we're just going to select the H2O and say 12 kiloelectron volts, recalculate, and your transmission here is this number here for the thickness here. So you can see that 100 microns is 97 and a change transmission. So some reasonable sample thicknesses. 1 millimeter is 76%. So at 12 kiloelectron volts, 1 millimeter is 76%. Okay. Actually, at the USAXS, we often use 4 millimeter NMR tubes. And the reason why we do that is because 4 millimeters NMR tube has a 37% transmission through the water. So it's basically optimal thickness, or 34%. I'm looking on the wrong number. 34% is the transmission of that. So that's pretty much optimum. Somewhere between 30 to 40% is optimum. Okay, so that's 12 kiloelectron volts. Then if we do 21 kiloelectron volts, what do we do at 21 kiloelectron volts? We do recalculate, and you can see that the water itself has 83% at 4 millimeters. We're not going to even try 1 millimeter because that's 84%. So that would be, if I do 1 millimeter, it's going to be a lot less. 95. So we can do 95. 1 millimeter is 95%. Okay. So the next thing we want to do, we have a chromium inside nickel. So this is basically transmission of nickel. So if we take nickel and go to 21%, at 1 millimeter of nickel, at 21 kiloelectron volts, your transmission is 3 times 10 to minus 11. It's completely unreasonable. So what we want to do is we want to go much thinner. So let's see 0.1. So it's 100 microns. And 100 microns of nickel is still only 9%. I told you we want to have above 20%. So we're probably going to need 50 microns. And 50 micron nickel sample is 21 kiloelectron volts. We need to get 0.05 millimeters. And that gives us a 30% transmission. If we take nickel and want to do 12 kiloelectron volts, things are going to be completely bonkers, because we're going to go in and you can see it's like 0.3%. So you would need to go much less. you would need to go to 10 microns. So at 12 kiloelectron volts, good luck making a sample, which is, you need 0.01 millimeter, and that will get you a 30% transmission. Okay. And next we need the PVA water. So in this case, it's 80% of water or some PVA, so we can more or less use water again. So we don't need to calculate, we already have those numbers up there because it's going to be pretty close to water. So we need water for the first set, we need nickel for the second set, and we need water for the third set. So we have the contrast and we have the transmissions and associated thicknesses. Okay, so now we can finally get to calculating something useful because we now have the parameters. What the modeling tool requires you to do or provide is a data on absolute intensity scale. Okay, so you need to model your microstructure. So for that we have a nice tool in IRENA, which is called modeling tool. You go to modeling tool, and in modeling tool you select this checkbox model. You go to data controls, you make sure you are using log stepping, and the predefined parameters here, that's 10 to minus 4 to 1 inverse angstrom, is pretty much covering beautifully the USAXS range. You select data controls and you add this in, and when you do it, you basically add fake Q scale. So this basically says I have Qs from here to there, 100 points, they're log spaced, so on a log scale here they look equidistantly spaced. That's all you need. You basically provided a Q scale. The next we want to put a model in. So we're going to go in and say, okay, here's my first model. And the first model is going to be, we're going to start with the gold nanoparticles in water. Gold nanoparticles in water. First thing is we set 0.1 volume percent. Scale is actually the volume percent. So that's 0.01 is the 0.1. That's a fraction, so 0.1 is 0.01. Then the contrast is the number we calculated, which at 12 kiloelectron volts is 10290. That's the contrast of the gold against the water. Then we can hit calculate model, and we can hit auto set. Now this is, let's just recalculate the model automatically. To make it simpler, I'm gonna make it in a Gauss, that I don't have to worry about much. And let's calculate a model number 1. So this is gonna be AU water, H2O, 0.01 volume percent. But we're gonna also assume that these are 5 nanometer particles, so that's 50 angstroms. So we're gonna make them into 50 angstroms here, and just this is somehow smaller. Okay, so this is a predicted scattering for 5 nanometer large, and this is a radius, so that would be 10 nanometer in diameter, 5 nanometer radius, 0.1 volume percent of gold in water, because it has the right contrast, it has the right size. We can make the size distinctly wider so we don't have those Bessel function oscillations. But this is what you expect from a spherical particle made out of gold swimming inside the water. Now what we want to do is we now want to store it in a folder, and we want to give it a number, an information here so we understand it. So this is RuH2O. We will keep the volume fractions the same, so we don't have to put them in there. This is 5 nanometers. Okay, I just save. Again, AU H2O, 5 nanometers, same. Okay. The next thing what we want to do is, just for the fun of it, let's make it larger. Instead of 5 nanometers, like make it 50 nanometers. And you can see it shifted the scattering to lower Q values. So we're not going to go in and save it, and this is AU in H2O, but now it's 50 nanometers. Let me just start this so I don't have to type it again. Continue, paste, continue. what happens is now we have these models in Igor. We're going to use them a little later. The next step is we now want to calculate the other one. So the next one we need to calculate is the chromium nickel. So let's, oh, and this is all done at, this was done at a contrast of, that's the 12 kiloelectron volts. So let me just add one more into it, rename. Oh, come on. Really? And this is 12 keV. And that is going to be 12 key. I forgot we need to do that also for the other one. So now if we go back and say that's 14,200, 184, that's the same thing, but now we can store it in folder. And this is now 21 kV. Continue. And then we're gonna go and make it smaller, and then we're gonna store it, but this time it's 5 nanometers, 21 kV. Okay, so now what we have is we have here scattering for 12 and 21, 12 and 21. Okay, the same we need to do now for the chromium. Now the chromium we can more or less ignore the difference in a contrast, so we'll just do 1 for chromium because there's not much of a difference in contrast. So the contrast is, let's call it 240, close enough. So it's 240, and this is 5 nanometers. The volume fraction is still 0.1 volume percent, so we're going to store this. And we're going to call this a, we don't care about the energy anymore, but we care this is 5 nanometers. And then we care about this is chromium nickel. Okay, chromium nickel. Continue, and we're gonna save that, and then we're gonna make it into 500 and store it, and we're gonna call that 50 nanometers, and again 50 nanometers. Now the last one we want to do is the PVA versus H2O. So for that one, the energy exchange doesn't depend on anything. 5.3 is the contrast. Now that one, this model makes no sense because those are not nanoparticles. So we're going to still do it the same way. Even though their 5 nanometers doesn't make any difference, we're going to just do the 50 nanometers and maybe even larger. So with this, we can, but we need to assume there is a 80% H2O and 20% PVA. So this is actually 0.2 because we need to use the minority phase volume fraction, PVA. So if there's 80% of water, it's really 20% of PVA scattering inside the water. So we now have a 20%, scale is 0.2 of this contrast here. And we're going to call it a 50 nanometer scattering here. This is our contrast. And we're going to store, we're going to call it PVA H2O, and this is 50 nanometer size. Let's just store it in a clipboard so we can continue and do that and continue. So now we have the PVA scattering. It's going to be, the scattering itself is going to be basically independent of the X-ray energy. So now we're done with those. We have all of that. These are now data. All of these things now contain data which are calculated on absolute intensity scale. Now, let's go to the tool I actually want to show you, which is in USAXS, there's a calculate scattering from model. And this little tool allows you to go in and select that you're going to use IRENA results. And let's start with the PVA. So we're going to pull the PVA in, and it pulls in the model of the Q vector and an intensity of the model. We're going to load it. And then we're going to hit update. And what you see here is, and you have a choice here, 21 kiloelectron volts, 28 kiloelectron volts, and 24,440. Those are the only choices now available. Now, The next what you need to do is, in order for this curve to make sense, is you need to go in and say, I need to also know the sample thickness, and I need to know what the sample thickness transmission is. So transmission at 21 kiloelectron volts, PVA transmission that's basically water. So we have 84% with 4 millimeters. So transmission is 0.84, but the thickness is 4 millimeters. And what you see is, you see the curve here. So the blue is the data themselves. The black is the instrumental background, and the red is how much your data stand up above the black curve. And so this is perfectly measurable, because you can see there are like 2 or 3 decades of intensity above the instrumental background. Notice that the choice at 21 kiloelectron volts there are multiple choices for thicknesses. You can see that this is 4 millimeters. 4 millimeters is 84% transmission. If we change this down to 1 millimeter, the intensity comes down because there's less sample volume. The transmission is a little larger, 95%, but it doesn't make much of a difference. Actually, it still comes even down. So you can see that while 1 millimeter sample may scatter, the 4 millimeter sample provides much better scattering signal to background. So if you just go in and change that to 4, and even if you change this to 84, it still doesn't make any difference. That means that you benefit from making the sample 4 millimeter thick. And to be fair, the optimum thickness for the water at 21 kiloelectron volts would be like 8 or 10 millimeters, which is not really reasonable. Anyway, if you have a 12 kiloelectron volts, I don't have a model for 12 kiloelectron volts, so we cannot do that. I didn't realize that. Anyway, if you decided you want to measure this on the high resolution mode, you can do high resolution mode, and that will look like this at 4 millimeters and 84. So you can see that you could measure this even on a 4 millimeter high resolution mode, which means you might be able to see some large structures in there. Next step is, let's go to measure, to model the gold. Or no, let's go to the chromium nickel. So if we go in and pull the chromium nickel, and let's say 5 nanometers, if you do 5 nanometers, and then we are looking we are at 24, the 24 and 21 are not too far apart, so we're going to use those. At 21, we need 30%, we have 30% transmission, so we get about 20% transmission at 24, but the thickness, in order to get through it, needs to be, where did we calculate that? There you go, 0.05. So if you look on this and calculate for 20% transmission at 50 micron thickness in a high resolution mode, you effectively see nothing. Okay, that's one of the problems of going to high resolution, is you are losing lots of intensity on getting the resolution. So what happens if we go to 21 kiloelectron volts? Even there, if it's 5 nanometers only, you may not see anything, because it's just all in the area here where the background is already quite significant. On the other hand, if we would select the 50 nanometers and update, you can see that you will see something in here which will provide you with measurable data. So this would be your 0.1 volume percent of chromium in a nickel measured at 21 kiloelectron volts. If we would just have to do 10 microns on a sample thickness, there's basically, again, practically nothing which you can see. It's going to be very difficult to see about the sample. So the sample thickness which we can get through is very important, as well as the transmission. Now for the gold, if we do gold 5 nanometers, and we're looking on gold at 21 kiloelectron volts, so that would be that's a very small volume, so we can probably do a thickness of 1 millimeter of water, and the transmission of that is probably going to be pretty much close to 90% or so. So you have a quite significant scattering here above your sample. So if you can calculate and show me this, yes, we can measure your samples very, very easily. If you then go to 50 nanometers, and you have to hit this update button quite routinely, then you are, and even if you can go and do maybe 4 millimeters there, you will be able to measure very nicely, even if your transmission is down to 0.8. You will be able to measure very nicely above the instrumental curve. And I will eventually add the 12 kiloelectron volts in the calculator for the next release. So some significant work behind the back to make it happen, but it will be eventually available there as a tool. But most users basically benefit from using 21 kiloelectron volts, where the instrument performs really, really well. It's very stable, it's very reliable, and at the same time provides with much thicker samples than you get through at lower energies like 10 or 12 kiloelectron volts. So you benefit a lot more from the sample thickness until you get down to like 30 or below 30% transmission, then the sample thickness kills you. So anyway, so if you need to know if your samples are measurable, what we did here today is we calculated the contrasts using the scattering contrast calculator for materials which contain no heavier elements than, you know, the standard carbon and things like that, and nitrogen. Then you don't have to worry about the anomalous calculator, but normally it's actually convenient to do it in anomalous calculator. Anomalous calculator will also calculate for you the sample transmission at the energies which we offer. So most likely, if you'll be planning on anything without, you know, having any special requirements, we would offer 21 kiloelectron volts. So you can go back and calculate how thick my sample needs to be for the energy which will be operating it. 21 is a good choice. After which you now know the contrast, transmission, and a sample thickness of your sample which you can live with. And then you go in modeling tool and calculate small angle scattering on absolute intensity scale. You save that as a result of the model, and then you use the scattering from model calculator, calculate scattering from model calculator in the Indra package, in the USAXS package, and you use that to calculate the amount of scattering. How much does it stand up above the instrumental background? Once you have that, you know, can I see it? How well can I see it or not? And then with those pictures and with those data, you may want to talk with us so we can plan your experiment well enough. Anyway, that's it. It turned out to be a little longer than I expected, but hopefully this will walk you through what you can do in order to get ready for your writing a proposal, or even contacted me for mail-in experiment. Okay, take care. Bye-bye.